Hi you, I'm glad that you come back for even more equality. Today we're going to look at how equality is an equivalence relation. That is, it's reflexive, symmetric and transitive. And reflexive we already know by design. Let's go back and look at the definition of equality in case we've forgotten. So we see that it's defined by being exactly reflexive. It's the smallest reflexive relation in fact. But what about symmetric and transitive? So for symmetry, we would like to prove that if we have x equals y, then y equals x. And that certainly sounds plausible, right? So how would we do it? Well, we have a p, which is a proof that x equals y. And we do the thing we almost always do. We pattern match on this p and see what it could possibly be. And surprise, it could only possibly be REFL. But if it is REFL, that means that x must have been the same as y, which means that it's not so hard to prove that y is the same as x anymore, because it's just the same as x equals x. So we can give the answer REFL here by pattern matching and saying that we're just in this. This is the only case we have to care about. Okay, so what about transitivity? This says that if x equals y and if y equals z, then x directly equals z, right? So we confuse these two things together. Okay, so we have a p which says that x equals y, and we have a q which says that y equals z, and we have to say that x equals z. Well, let's do the only thing we can do, which is the pattern match, and this time we have two choices, but it doesn't actually matter which one we choose. So I'm going to choose p. A pattern match on the p. Oh look, it could only be REFL. Well, that changes things. That means that x is the same as y, which means that the type of q, which used to be y equals z, because x is the same as y, this type now becomes x equals z, right? Which is exactly our goal. So I can just return the q in this case. So I pattern match on the first one and I return the second one. Alternatively, if I wanted, I could also pattern match on the second one, in which case I can return REFL. It's kind of nice not to look at things unless you have to. So just return the key without looking at it. Okay, so that shows that equality is reflexive, symmetric and transitive, which is nice to know, but also very useful many times. And it also has one more property. It's not just any old equivalence relation. It's a very special one. It's the least one. And the property it has is that if we have any set A and any property P of elements of A, if I now have two elements, x and y, and I know that they are equal, and if I know P of x, then I also know P of y. So all properties respect equality, not way to phrase it. Or you can't tell apart equal things, right? So how would we prove this? Well, let's see. This is what we have. This is our goal. Well, there's only one thing we can really look at, and that's the p, right? So let's look at the p. Well, there's only one case. It must be REFL. And if it is REFL, then our z is a perfectly fine p of x, even, or p of y, even though it was just a p of x before. But looking closer at the p, we realize that x must be the same as y, which means that p of x must be the same as p of y, and this can just become the identity function. So what have we learned? Well, equality really is an equivalence relation, and we are going to use these things all the time, especially symmetry. And we can substitute equal things for equal things. In the next video, we're going to look at a small case study where this is actually useful.